So that's what we wanted to prove, right? That U1 equals U2. Now, what did we assume up front, right? We assumed this growth assumption on U sub y. We can drop that, okay? So let's now drop this growth assumption, okay, on U sub y, okay? And we're going to introduce this function z sub r of y, and it's going to be equal to 1 where y is less than or equal to r. It's going to be 0 for, let's say, y is greater than or equal to r plus 1, and it's going to be smooth in between, okay? So it's going to look like something like this, right? So we have, here's minus r and r, here's minus r minus 1, and here's r plus 1, right? Here's y, and here we plotted our functions. Zr, okay? All right, so it's kind of like an indicator function, a smoothed indicator function. So Zr is C2 on R, okay? And Zr of y, right, is bounded from above by something. We'll call it L. Zr's derivative, we'll say, is bounded by that same thing. And Zr's second derivative is bounded from above by that same number. So we just pick this number L that is an upper bound on the first, second, and 0th derivatives, okay? So now all we're going to do is we're going to use ZRY VY tau instead of VY tau in our proof, okay? And this basically avoids the problem that we might run into with, having unboundedness, way out at the boundaries, like when we take R to infinity, right? And in those integrals that we're comparing. So if we do that, then we get U ZR V sub tau plus K times U Z sub R V sub Y minus U sub Y ZR V. And again, I keep writing U when I mean to be writing W. So every time I write a U here, just assume I mean W. Okay. All right. And this is equal to KW 2 ZR prime VY plus ZR prime prime V, okay? Integrate over where V has support, or sorry, where U has support, R plus 1 for R greater than X, absolute value, and for tau is between 0 and T minus epsilon, okay? And then using the same reasoning for Z sub R Y is equal to 1, as long as Y is less than R. And we know that in this range, ZR prime and ZR prime prime is equal to 0, right? Except on R is less than Y, is less than absolute value of Y is less than R plus 1, okay? So essentially in this case, we can prove, right, that if we integrate this system here, right, from 0, or sorry, from minus r up to r, right, then we're going to get everything vanishing except for the integral of w against v in this case, right? So if we look back here, right, the thing that remained here was this term here, right? So this wv tau term. So when we integrate that, again here, the only thing that should remain here is this term here, okay? And this again will imply that in the limit as epsilon goes to 0, right, of the integral from minus infinity up to infinity, okay, of w, so now it's going to be w of y t minus epsilon phi of x minus y epsilon, and now we have this additional thing z of r y here. It will be x minus y, okay, dy. This is going to equal w of xt, and we can say that's equal to 0, and so ultimately that u1 is equal to u2, okay? So similar logic there. We have to do, you know, a little bit more work because we're involving this indicator function that basically removes the effects of having the function be unbounded, right, potentially, or not well enough bounded as we go out to r goes to infinity, okay? But again, we get this uniqueness result for solutions to the heat equation on the real line, okay? So for the heat equation, just to sum up, it's the canonical parabolic equation. We can use the fundamental solution in order to get general solutions to the initial value problem. If we have a quarter plane problem, then we have to use these odd or even methods of reflection in order to get the solution. If we have inhomogeneities, we can use Duhamel type principle. And we can either use an energy argument or the maximum principle in order to get uniqueness, or this more nuanced version of the uniqueness proof in the case of unbounded domains. Okay, so that's the heat equation. You'll get a chance to